Welcome to our presentation on the identification of lifelike characteristics of human crowds through a classification task. I'm Martyn Amos, and this is joint work with Jamie Webster, who was my PhD student at Northumbria University in the UK. So this is an artificial life conference, and a significant amount of A-Life research focuses on studying the collective behaviour of mobile agents operating in a spatially explicit environment, whether that's 2 or 3 dimensional. And of course we're all familiar with the classic example of Craig Reynolds Boyd's, but our group has recently worked on simulating collective behaviour in a range of systems, from swarm robots to bacteria and social insects. And in all of these examples, agents may move around and interact with their environment and with one another, generally under the control of a movement model that defines the rules and constraints under which they must operate. And of growing interest to our group is the study of human crowds. So here we see a time-lapse movie of a crowd leaving Wembley Stadium, not, I have to say, after the recent Euro final. And we can see how a simple and compelling abstraction of the crowd could be to think of it as a fluid. And indeed, early computational studies of crowd flow were based on the equations of fluid dynamics, but as we'll see, this is often insufficient to capture the diverse dynamics of the crowd. So why does this matter? Well, crowds are ubiquitous, and understanding how the crowds behave and how they can be managed is crucial to the operation of events, to urban design, and to the prevention of disasters. So here we see the Love Parade disaster, in which poor crowd management led to the crushing to death of 21 people. And of course we're familiar with many other examples of this, the Hajj being another example, and the Hillsborough disaster, and so on. And of course, over the past 18 months, the crowd has taken on an entirely new significance as the crucible of COVID, and agent-based simulations have lain at the heart of epidemiological modelling and government responses to the pandemic. So by 2050, nearly 70% of the world's population will live in cities. We are now most definitely living in the age of the crowd, and we need to understand and mitigate the impact of crowds on infrastructure, safety, security, and quality of life. So we need to understand the crowd, but it's often extremely difficult to perform large-scale experiments with real human participants for legal, ethical, and safety reasons. So as with many other complex systems, we approximate their behaviour with simulations, generally of the agent-based variety. And these have been used very successfully to design public spaces, to manage events, and to understand the internal dynamics of crowds. And here we see a screenshot of Behaviour, which is one of many crowd simulation tools available, and which is the one that we use in the current work. So fundamentally, we're interested in 2 aspects of the output of a crowd simulation: its validity and its believability. Now these might sound like the same thing, but they're subtly different. Validity is measured in terms of how closely a simulation's output matches observations taken in the real world. Believability is a little bit more slippery, as it concerns the plausibility of a simulation's output from the perspective of a human observer. Importantly, here we're not talking about photorealistic Hollywood CGI believability, but about whether or not an observer can detect patterns of behaviour that are somehow implausible or unrealistic. So why does this matter? Surely it's enough for a simulation to be valid. Well, quite often, yes, we might be satisfied with a valid high-level outcome, for example, the total time taken to evacuate a stadium, without worrying about microscale properties of the system. But it's precisely those little eddies in the flow, the stop-start unpredictability of individuals and so on, that render a crowd realistic, as we'll see. So crowd simulation still meets with a fair bit of resistance from decision makers, and we've argued in the past that this is at least partly due to a lack of trust, due to a perceived reality gap. So if we can close this gap, then it may eventually lead to increased trust in and uptake of these sorts of techniques. So all crowd simulation packages have an underlying movement model, and the most commonly used is the social forces model, or SFM, which is a very well established microscopic continuous model which uses attractive and repulsive force fields between individuals and between individuals and their environment to guide movement. So the SFM provides the base movement model for a number of pedestrian simulation packages, including FDS EVAC, PedSim, SimWalk and Mass Motion, and it's been used extensively in movement research and validated using real-world data. So here we see it being implemented, and although the high-level outcome of the simulation may be valid, I hope you can see how the movement of individuals appears rather uniform and quite artificial. It certainly doesn't look particularly realistic, and it's precisely this problem that we're trying to address. So the current work builds on this recent paper of ours from last year in which we presented our Turing test for crowds. So I probably don't need to spend too much time explaining the Turing test to this audience. Essentially, our participants were presented with rendered movies that represented either the movement of real crowds or of simulated crowds, and their task was, for the first group, to identify the real crowd in a number of pairwise comparisons, and then secondly to classify individual movies as either real or simulated. And we use this same basic setup in the follow-up work that I present here. So we'll take some time to explain it now, as well as our original findings, as they actually motivate what we did in this paper. So we used publicly available data taken from the Edinburgh University Informatics Forum, which is a space with multiple entrances and exits, and we show a diagram here. So footage was recorded by an overhead camera over several months, and individuals were extracted, individual trajectories were extracted, and we used the final trajectory data that was made available and built some tools to query the data set and extract, for example, clips containing a certain number of people in a set period, as well as a customized rendering engine to display both real and simulated clips in a uniform manner. So we essentially chose a bunch of real-world clips taken from the Edinburgh dataset, and then extracted the number of people visible and the entry time and the entry and exit point distribution and so on, and then basically simulated those scenarios. So for each scenario we had a real clip and a simulated clip, which were both similar in terms of the number of people present and the rough distribution of the exits that they entrances and exits that they used and so on. But we wanted to make sure that the simulation was actually producing valid outputs in terms of the overall crowd movement. So we ran it a number of times for different crowd sizes using the observed times and distributions that I've just mentioned, and we used two metrics to establish the validity of our simulations. We used average nearest neighbour distance, which is a measure of clustering in the crowd, and polarization, which is a measure of order in the crowd. And definitions of both of these are supplied in the paper. So we basically ran the simulation a number of times for different values of crowd size from 3 up to 27, and then averaged the values of those metrics. And in order to make sure that we weren't introducing biases by using a specific package, we ran the simulations using both Behaviour, which is the main package that we use, but also PedSim, which is an alternative. And obviously we calculated the values of those metrics for the real crowds as well. And what we see is that the both simulations produce outputs that are broadly in line with what we see in the real crowd. So we can have some confidence in the validity of our simulations. So here we see an example test where one of the movies represents a real crowd and the other represents a simulated crowd. Try to see if you can tell which is which. Which is the real crowd, which is the simulated crowd. So the one on the left is simulated and the one on the right is real. So below the movies we show the results of two trials. The first is the comparison trial, which was conducted with 6 pairs, so the maximum score was 6. And the second, with different participants, is the classification trial, in which people were asked to classify as either real or simulated 12 individual movies. So the maximum score there was 12. Notably, when people were asked to choose between two movies, the most common score was 0. That is, a significant proportion of our participants were able to perfectly distinguish between or partition the real and simulated crowds, but they were totally unable to tell which was which. So classification performance was slightly better, but it still didn't outperform random guessing. And we asked our participants for informal feedback on features that they'd used to try to identify the real crowds, and this is the sort of thing that they said. Overall, they thought that simulated crowds were too random and messy, and real crowds moved more smoothly. Actually, the opposite was true, and the collision comment was particularly instructive, as the social forces model explicitly tries to keep agents from bumping into one another. So that laid the foundations for the current follow-up study. So we confirmed the existence of a set of features of real crowds that allow individuals to distinguish, if not identify, those real crowds. Our hypothesis is that new participants will show an improvement in classification performance after being trained by viewing movies of real crowds. Once they've explicitly identified the features that allow them to identify the real crowds, that tells us what we need to include in the new versions of our crowd simulations in order to make them more realistic. So here's our protocol, which is largely modelled on the original Turing test we've just described. The major difference, due to the fact that the experiments took place at the height of the pandemic, was that it was conducted online as opposed to in person. But this probably gave us a more diverse pool of participants. In the first trial, we just used university students in their lectures. So we did the trial before their lectures. So we recruited 232 people online, all of whom took a new version of the 12 movie classification test, and that gave everybody a baseline score. And then we allowed a few months to elapse in order to ensure that there weren't any sort of recency or learning effects. And we then asked people to participate in the second test, and we offered them a £10 Amazon voucher as an incentive, and 50 people accepted our offer. So remember, these 50 people each had a baseline score from the original test, and we then trained them by asking them to watch 6 movies that were explicitly labelled as representing real crowds. And then they had to do a second classification test. And this time they were asked to specify any features of the real crowds that allowed them to spot the real crowds. And the test is still available online if you want to give it a go yourself. So we first checked that the smaller group P2, 50 participants, was representative of the larger group, and we found this to be the case, and the details of the analysis are in the paper. We then looked to see how classification performance changed for these 50 participants between the baseline and the second test after training. And we saw a rise in the average classification score from 27% initially to over 60% after training. And to the right, we see a slope graph plot of individual performances, where a green line shows a significant improvement, purple is neutral, and red shows a significant drop in performance. And as you can see, the plot is overwhelmingly green. So these results confirmed the first part of our hypothesis, that suitably trained individuals are able to correctly identify or classify real crowds. So we then analysed the free text in order to specifically identify those signature features. So we performed manual analysis on the corpus of 50 submissions and broke it down into a number of thematic atoms, which we've tried to present here classified by crowd type. And we immediately noticed two themes that were mentioned much more frequently than others: that real crowds are more unpredictable or erratic, and this made up 21% of all atoms, and that simulated crowds move much more smoothly, 16% of all atoms. And these observations are clearly complementary in that after training, observers believe that real crowds are more unpredictable than simulated crowds, which move much more smoothly. However, it's not sufficient to simply analyse the frequency of themes, since dominant features may not necessarily correlate with good classification performance in the participants who identify them. We need to extract the features that have been identified by the participants who perform best. So we first consider relative changes in scores and then look at the absolute changes as each perspective yields insights. So here we plot each theme against both their frequency of mentions and the average relative change in classification performance of participants who specifically mention that theme. So we notice from inspection a cluster of themes that are relatively infrequently mentioned, fewer than 10% of the time, but which are associated with significant improvements in classification performance, so S3, R4, R1. However, we see that the two themes that are mentioned with frequency greater than 15%, that is S4, smooth continuous movement in simulated crowds, and R2, unpredictable movement in real crowds, are both also associated with performance improvements of around 400%. And as noted earlier, these themes are complementary. So this finding is entirely consistent with our earlier informal narrative results, where participants who had flipped the real and simulated crowds believed that erratic movement was characteristic of fake or simulated crowds, and that real crowds moved smoothly and predictably. After training on real crowds, however, the participants in this second trial correctly identified that real crowds are actually more noisy and unpredictable, and that overwhelmingly smooth, predictable trajectories are characteristic of simulations. So we now consider some absolute changes in classification score between tests, and we see roughly the same clustering of labels as before, but here we would draw particular attention to the albeit infrequently mentioned themes that are correlated with reductions in performance. That is, the features that are mentioned by participants whose classification performance got worse after training. And the two features to which this applies are S2, rapid direction speed changes in simulated crowds, and R7, collision avoidance in real crowds. And again, these findings are entirely consistent with both the current results and our previous study. If high-performing participants correctly spot that simulated crowds move smoothly, then it's entirely to be expected that low-performing participants will incorrectly ascribe S2 to them. Collision avoidance in real crowds, R7, is also specifically mentioned in our previous study. Participants who performed badly assumed that individuals in real crowds would naturally avoid one another, and in fact, the real dataset contains numerous examples of individuals coming into close contact. So we conclude, therefore, that the primary feature of real crowds that allows trained individuals to correctly distinguish them from simulated crowds is their higher degree of unpredictability in terms of individual trajectories. A secondary feature is collision avoidance, specifically proximity. Based on this work, our main suggestion, if what we seek is lifelike believability in crowd simulations, is that models should include the facility to add noise to the movement of individual agents. Surprisingly, this feature is not generally provided in simulation packages. Models might also benefit from a relaxation of collision detection radii to allow for closer proximity of agents, and in this way we might easily replicate the appearance of at least some of the micro-level behaviours that have been highlighted by some crowd theorists. So in terms of limitations and future work, the underlying crowd dataset is based on a relatively small physical space, which is quite regular in nature, but we do point out that it's actually much larger than the arenas that are used for artificial crowd experiments. Moreover, the observations have a high level of ecological validity, as the recorded pedestrians were not consciously aware of being participants in any experiment. Our second test used a relatively small number of participants, but we've established that they were representative of a larger set. And finally, our findings are really only applicable to routine crowds, that is where people are going about their everyday business, and not to emergency or evacuation crowds, where behaviours might be very different. However, there's still significant value in updating simulations of such routine crowds to render them more lifelike, especially if important policy or design decisions are to be made based on how they're perceived. So this study has provided empirical evidence to support the inclusion of relatively straightforward modifications to any and all of the movement models underpinning both scientific and commercial crowd simulation packages. Importantly, the addition of noise to individual trajectories and the relaxation of collision detection radii are entirely generic updates, but ones that could significantly improve the believability of crowd simulations across a range of applications. So our future work might include the automatic detection of features of real crowds from larger and more complex data sets, the consideration of the impact of changing movement model parameters, and the integration of identified features into commercial crowd simulation packages in order to test their impact on believability and thus close the circle. So we thank all of our participants for their involvement. We thank Manchester Metropolitan and Northumbria Universities for supporting Jamie financially, and Goethe Costa and the Videri team for very useful discussions. All of our experimental materials, the code, the simulation code, the analysis code, the movies, the datasets and so on, all available at this link, and we thank you for listening.